Today we'll be going over annuities. And up until now, hopefully people are familiar with the language, which is the most important part of differentiating these problems. More specifically, when we've worked with whether it was simple interest or compounded continuously, there was a sense of deposited, past tense. So think one time, or the notion of a one-time deposit. So introducing annuities here. The purpose of them is essentially to allow for multiple equal contributions towards an investment of some sort. And I'll write that down. Annuities allow for multiple equal contributions towards an investment. Okay, and there are two annuities that we have to face. So we can call this a definition. And then we can say annuities can be categorized as future or present. The following equations are okay, and future will italicize here, and present will italicize since we're going to acknowledge that. The first of the formula will be the future value annuity. This will be written down. However, you want to think of this as an investment of some sort, something that you're going to be saving towards the future, essentially. And here's that equation. Future value one plus I for CP to N times CP minus 1 all over I divided by the CP. So that's the future value version. The present value is a very similar looking formula, except it is altered in this sense. I divided by CP. The unique thing here is to watch out for the negative sign in the exponent. Of course, we're going to discuss that in a moment. I simply like to bring it up right from the beginning because it is something that combatants students a lot when they're calculating via their calculators. These are the two formulas we have right here. They are the future value and present value. And the one thing to note, if you notice, is that if you ever have seen either a previous video or any of my teachings or notes at some point, you'll notice that normally I leave the formulas in a general form without the compounding period. Per request of student feedback and acknowledgement, I've now integrated the compounding period into the formulas themselves. So they may look a little bit messy, however, I'll talk about them at each step of the way. Now let's discuss the variables and their meanings. The good news is that they're pretty much the same in the regular compounding period problem, except the difference is that this is annuity, and again, the reason for annuity is for multiple contributions. So I'll write here where I'll separate it where future value account. What I'll do is I'll separate them by color here. PV is the present value of account. And then the rest of the other variables are the standard variables for compounding period. And what I'll do is I'll note that they share both of them. So you can see here that this is what they both have individually, future on the left, present on the right. However, they both share the following: a compounding period, they both also share the several variables right there. R is new. The best way to think of this is R is for recurring. Or reoccurring, whatever way you like to say it. Occurring payment or deposit. It's the same thing, right? The point is that previously we would always have a P for principal, principal value, principal balance, whatever the case may be. Now with this R, hopefully it can be registered as one would study this, realizing that R is something that's reoccurring or recurring on a systematic or some type of frequent basis as opposed to one time. So R is new, quote unquote, in that sense. The others are the same. I is for interest rate. Misspelled interest there. Interest rate. And then N is essentially time. Again, I'll write it in quotation marks, so that's the easiest notion to think of it. Formally, though, it is the total number of compounding periods. Total number of compounding. So not the compounding period itself, just the number of compounding periods. And compounding periods. Okay. We won't get into it this video because there has to be a separate one, otherwise the content becomes way too lethargic and long and tedious. Things that I will note though is that even though there are, depending on the way you're looking at the formula, if you're looking at the future value, there's 1, 2, 3, 4, 5 variables. If you're looking at the present value, there's also 5 variables. The good news is that I'll note right now the only variables you can solve for are the future value, the present value, and the recurring payment. In fact, I'll note that right here and I'll type it. So I'll go note okay. When annuities are involved, the only variables that may be solved or asked for, and I'll italicize that so it's very apparent, are the following. And I'll write this in black. There's the future value, the present value, or the recurring payment. And I'll italicize these so that they're variables. Okay? And that wraps up the introduction of the annuities. We're going to do 2 examples, one of a future value annuity and one for a present value annuity, and I'll notate that when I write the examples as well. So here comes our first example. I'll call this example 1. And in parentheses, I'll call this a future problem solving for the future value itself. and then I'll underline this, and then we'll be ready to go. Okay, here's the problem itself. Suppose you want to put away $200 every month for the next 30 years. The account is paying 3.14% compounded monthly. That's the beginning information. Now come the actual questions about the problem. How much is in the account after maturity? How much interest was accrued? Okay. If you're used to my nomenclature as how I attack these problems, the first thing I'll always ask is what are keywords, our hints, and whatnot. Here you can see that it's compounded monthly, which I'm going to underline, and I'm also going to draw a little arrow here, or try to. There we go. Actually, I'll draw it this way. Compounded monthly, so you know that the compounding period is immediately 12. Up until now, the finance equations that we have to work with were only simple interest, compounded interest, compounded continuously, and effective interest rate. Effective interest rate is kind of its own thing. But the point is that the compounding period is the most pertinent because I would always say or always ask, what's the compounding period and which formula do you have to worry about? The thing though is that knowing the compounding period here is not enough. You actually need to pay attention a little bit more. And the key word here, I'm going to underline it right here, is this: put away $200 every month. More specifically, the every month portion here. That's how you know it's an annuity. Because if it was a regular compounded interest equation, it would say you would deposit $200 or $200 was deposited. Some notion that it was one, in the past tense, and two, one-time thing in the past tense. Here we can see that there is a recurrence here of every month. So therefore you know it's the annuity. Since the question is asking for how much is in the account in total, as I alluded to earlier, we know that we're going to be using the future value equation, which I'm going to write again right here. This time a little bit quicker. And then this time with the compounding periods there too. CP minus 1 all over I over CP. Okay. Now we can list our variables. The future value is what this problem is asking for. The recurring payment is $200. Okay, the interest rate is 0.0314, and N here is 30 years. You may have also noticed that I didn't divide the interest rate by the compounding period, nor multiply the time by the compounding period. The reason is that since we have the formula introduced now with the compounding periods integrated into it, one could follow easily just to literally make sure that every formula or every variable is accounted for. So punching this in or writing this in will look like the following. We have $200 bracket 1 plus 0.0314. I'm still going to color code the compounding period in green because that's the most apparent to me in introducing this. For some students, you could write this as 30 times 12. Some people like to do that calculation immediately. If you do, you can do it on the side here and realize that this is 360. So if you don't like having to multiply in the exponent, you could realize that this number right here, you can enter 360 immediately and you'll get the same effect. minus 1, close the bracket, and then on the bottom here, 0.0314 divided by 12. Now this is where it gets rather tedious, not because it's difficult, because we have to worry about parentheses and order of operations and all that jazz. However, if you write it in the way that I'm going to write now in terms of calculator syntax, you'll get the formula correct as well as the answer every time. So for the calculator itself, this is how it's going to look like. I'm going to write calculator here. Actually, I should write calculator syntax, so that's more apparent. Okay, how do we go about this? This is what I would do. I would write 200 first and open 1 parentheses. And again, I put them in boxes so that people are aware that you're either punching this in a calculator, again, a scientific calculator that has all the syntax written out as you're writing it, not one that disappears, or if you were going to type this out manually via a web browser. You have 200, you got to open parentheses for the entire numerator, then another parentheses. Here you can go 1 plus 0.0314 divided by the compounding period, which is 12. You're going to close the first set of parentheses. This allows for the inner part that's similar to the equation for just compounding period. We're going to raise to the 360, since I could do that immediately in my head. Now, depending on your calculator, you have to be careful here. It's raised to the 360, and you're going to subtract 1. Not 1 from the exponent, 1 from the entire expression of 1 plus 0.0314 divided by 12, raised to the 360. So on your calculator, you either have to, depending on your syntax, if the blinking cursor is still in the numerator, you have to push right, quote unquote, right, so that the cursor goes away from the exponent to the bottom. Most calculators do that automatically. However, when I write minus 1 here, that is not to be included in the exponent. And close parentheses. Okay, so going through this, I tell students to calculate the numerator, then divide by the denominator as 2 separate steps, because then that allows less room for error. So after all of this, you would write equal sign, and you would get your answer. So again, this provides some type of answer. So you can think of this as step 1, which I can write here. Step 1. Step 2, without clearing your calculator, please make sure you don't clear the calculator. You have to divide by the denominator. Now the problem is that the denominator is the interest rate divided by the compounding period. So you can't divide one at a time. You have to divide it as a whole because you're dividing the entire fraction. So after you do the numerator, which was that first step right there, and you hit the equal button or equal sign, you get an answer. Without clearing the calculator, you would then hit the divide symbol, the parentheses symbol, and then 0.0314, and then divide by the compounding period. 12, close this parentheses one more time, the equal sign, and then now this is answer to the problem. Answer to the problem. At least the first half of the problem. And then up here you could think of this as, I guess, not the answer itself, but sub-answer, I suppose. Put that in quotation marks. Okay, so what's our answer here? The future value, again, this is already rounded since I already got the answer in advance. It's 195,435.87. And if you're curious, asking, how does this make sense, or does this even make sense, or am I on the right path? You can think of it this way. Well, how much do we deposit every month? $200. You're depositing $200 away every month for the next 30 years. So if you take 200 times 360, which is, actually I can do that separately on a calculator here. 200 times 360, you get 72,000. So you can imagine that the future value plus what it amounts to from 72,000 and then the interest that you would make, it better be a lot more than, well, 72,000 for that matter. But the idea is that whatever you're depositing, the way I like to describe it is that the recurring payment is your pocket money, if you will. This is money you're physically putting away every time, every month, every period, whatever the period may be asking. So anything else after your pocket money, as I describe it, is interest, earned interest. So the next question is, how do you find the interest earned? Interest earned is not a formal formula. Interest earned. But you can think of it that way if you want. So here, for the future value, it is essentially the future value minus the recurring payments times how long, and then you can't forget the compounding periods. Now, why is that? The problem is that students generally take the future value, which our answer previously here was the 195,000 and 435.87 cents, but basically about 195,000. And what they'll do is that they know they can't subtract just 200 because you didn't deposit $200. The number one mistake students generally do when looking for the interest earned is that they take the future value, they subtract 200 times the time, which is 30 years, which is partially correct because you did deposit $200 for 30 years. But did you deposit $200 30 times, one for each year, or every month for those 30 years? And that's why the multiplying by 12 comes in. In any event, I did that answer again in advance, and I got 123,435 and 87 cents. So this is the interest earned and with the formula as well. Well, not a formal formula, but a strategy for finding it. So again, future value is how much is in the account after maturity, $195,435.87. And then the interest earned is that same future value subtracting what you deposited every month. So it's not 200 because it wasn't one time. It's not even 200 times 30 because you didn't put $200 away once a year for the next 30 years. It was actually $200 every month for the next 30 years, which is that 360. Okay, that wraps up the future value problem or example, solving for the future value itself or future value variable. For the next one, our second example, this will be, as you can imagine, example 2. This is present value problem. I want to say solving for PV, which is present value. I'll italicize that and underline all of this. Okay. So here's the problem now. It's asking for, suppose, or I'll say consider a loan. Okay, you can afford to pay $100 per month for this loan. Let's say supposed loan. Okay, a bank is willing to offer a 10-year loan at 3.14% compounded monthly. The question is, how large of a loan can one afford? Can you afford? and then how much interest is being paid over the 10 years. Okay, that's good. And then what we can do is, yeah, that should be fine. All right. Same hints, right? This one will move a little bit quicker or a little bit swifter. So you can see compounded monthly, same thing. Have the compounding period right here being 12. And you know that it's a present value annuity solving for the present value. How do you know that? Well, they told you that you can afford to pay 100 per month. If you can afford to pay 100 per month, that sounds like a recurring payment to me, or some type of recurring basis. And what happens is that with the recurring basis or payment, however you want to think of it, you know that that's immediately your R variable right there. So since you are given or provided an R, you must be solving for the present value. Can't have both variables empty. Okay, and again, I'll rewrite the formula here. The present value is R times 1 minus 1 plus I over the compounding period, and again, the negative compounding period in the in the numerator right there. Okay, so our variables are the present value, which we're looking for. R is $100. The interest rate is, I use the same one just for simplicity's sake, 0.0314. And the time here, I change it to just 10 years, so think of it as a short loan or short-term loan, okay? Punching in these numbers, we get the following. We get 100, okay? And then you get 1 minus 1 plus 0.0314. Here comes the compounding period. Divide by 12. And again, if you are able to do this calculation in advance for the time, you know that that's going to be 120. Well, here in the formula, it's going to have to be a negative. Remember that negative sign up there? 120. And we'll touch on base on how to calculate that. 0.0314, and then divided by 12 as well. Now, what does this calculator syntax look like for this type of problem? Well, normally, with that negative right there, I teach students to go one at a time. I suppose I could have done the same for the previous problem. However, it's relatively straightforward in terms of understanding the calculator. Here, though, actually, I wonder if it's easier. Yeah, I'm going to write out the entire numerator because normally if everyone has a calculator, I would say calculate one piece at a time. The thing though is that I know that some students, they're writing this out verbatim. And if I write this out verbatim or as is on a calculator on an internet browser or whatever the case may be, you don't want to calculate one piece at a time for this. Okay, so this is how I'm going to do it. I'm going to do the numerator first and then the denominator second. So similar, step one, you're going to go 100. Okay, technically there should be a multiplication symbol here, but most calculators will understand if you open the parentheses immediately. So there's the parentheses, and then you get 1 minus, you got to open another set of parentheses here. Now this is the inner parentheses here, 1 plus 0.0314 divided by the compounding period. Okay, and then we're going to close the parentheses. And again, this is similar to that where in the future value we got to raise, but here you have to raise to the negative 120. Normally I write the little negative symbol here, but I don't want students to get confused with the negative symbol for the minus. So I'm going to write, after the caret, I'm just going to write negative 120 so that people are aware. And then you can close your parentheses here, and then hit the equal sign or equal button. And again, this provides a sub answer. I mean, I'm using that very informally, but sub answer. So it's the answer on the way to find out our final answer. So again, you would hit equal sign, and then you would not clear your calculator because you're going to use it now to calculate the denominator. So after you get the entire numerator, you hit the answer there. You, same fashion, you hit the divide symbol, open the parentheses because you're dividing by the entire fraction in the denominator, and that's 0.0314. Divide by the compounding period, which is 12, and then equal sign here. And then this will provide our answer to the problem again. Answer to problem. Now, of course, again, I did this in advance. So the answer that you should have gotten practicing this is the following. Present value is $10,287 loan and 18 cents. Now, what about the interest paid? The unique aspect of this problem is that you took the time to find a big number, if you will, in this case, a present value. But remember, this is the amount loaned to you from the beginning. That's why they call it a present value annuity, because what value were you loaned from the beginning or from the present? And your payments of $100, that actually includes the interest. So it's going to look very similar to the interest above, where we had the future value minus the recurring payment times N times CP, right? Or FV minus R and CP. Again, not a formal formula you have to worry about. It's just thinking about how interest and subtracting works. But it's going to be the other way around. So it's actually going to be the recurring payment. In this problem, I made it purple, so I'll just put it that way, times N times the compounding period. And this is going to subtract the present value. Again, why is this? The recurring payment, when it says, hey, you're allotted or you can afford to pay $100 every month, that is paying back not only the loan, that's the loan plus interest. So if you think about it, the loan amount plus interest of $100 paying over 10 years, 12 months at a time, right? That's going to be more than what you originally loaned. So as you can see here, this answer is going to be $1,712.82. Again, this is just the interest paid, right? In total, you're going to be paying back a lot more. How much more? Well, it's whatever this part is here. So I'm going to write as a note here, if you're curious on how much are you paying back in total, even though that's not a question for this problem, but amount paid in total is actually just this component right here. But that makes sense, right? If you take $100, multiply by 12 months, right? 100 times 12, and you do that for over 10 years, that's going to be more than the original amount loan because you had to pay back the loan plus interest. Okay. Another way you can think about this is that I'll wrap up by saying from our textbook, it states that you can always recognize when it's a future value or a present value problem for the scenario that you're in too. So I'll write that really quick here. Hints for future value versus present value. So here, you know that The future value is some type of investment, a savings, think 401k. And the way that the textbook acknowledges this is that you can think of this as a lump sum or big money, or however you want to think of it, lump sum later, because you're going to get that large amount later in life after the number of years of depositing. Whereas the present value, you can think of this as a loan, a mortgage, and then in terms of the lump sum is granted to you now, right? So as you recall the first two examples, right, it asked you how much was in the account after maturity for the first example. That was a lump sum you're saving towards in the future that you're going to have to take out after 30 years. Whereas the second problem here, this is a loan. You're considering a loan. When are you going to get issued the loan? When does a student get their loan for student loans? It's issued now, in the present, that you're going to pay over time. Okay, so those are our two examples for future value and present value. We'll have a second video addressing how to solve for the recurring payment for both, again, future value and present value time, or present value or future value annuities. Thank you for tuning in.